All right. So, right. So, problem set 6 is due next week. We'll have our problem session to discuss it. And as I mentioned, there won't be an assignment that you're required to do over fall break, but I was just looking back, and there's some material that would be nice if you felt like it. Give it a shot. It'll be extra credit. Yeah.
There will be no problem session for 7 today.
So our next Thursday and Friday is fall break.
Right, so no problem session for 7.
No, so there won't be. Yeah.
That's what we're doing this week. That's one of the talks.
All right, very good. Okay, so the last time we were talking about this notion of a dark state in the absorption of electromagnetic radiation when you have multi-level structure atoms or matter in general. And we can see this kind of explicitly if we look at this kind of configuration, for example, the lambda configuration, where we are driving the system with these two colors, and in this case I'm choosing them to be on resonance, although that's not really so important. We'll come back to that with the excited state. Okay, so there's two colors, lasers, the colors omega L1 and omega L2, and we have our interaction Hamiltonian. And that interaction Hamiltonian is the dipole interaction, which in the rotating wave approximation takes this form in the rotating frame. And so if I just look at the matrix element between the ground state, which is considered to be some superposition of these levels 1 and 2. Okay, so I'll call that sort of a general ground state. Levels 1 and 2 might be two sublevels within the electronic ground state. Okay, and I look at the matrix element between them. Then, well, if I look at that for this kind of state, what I see is that I have a term that depends on this amplitude and the Rabi frequency that's associated with that interaction. Sorry, that's a plus, the minus sign is there. And then this amplitude with that matrix element, okay? And that's interesting. So there exists a state, which I'm going to call the dark state, which is the state for which this matrix element is 0. Okay. So if that off-diagonal matrix element is 0, then that state is dark to the light. There can be no absorption because there's no matrix element that couples that state, the excited state. And that is the state where C1 omega 1 plus C2 omega 2 is 0, or C1 over C2 is equal to minus omega 2 over omega 1. Okay? So this particular superposition, which has omega 2 in level 1 and omega, this guy normalized, is the dark state. Okay? I'm getting very confused with Omar sitting over there. Yeah.
When you say dark, he says dark with respect to laser mean that it's not going to end up fluorescing because it's not.
It means if I am in this particular superposition, it will not absorb. the atom will be completely transparent. It will just, the atom will be dark to the light, and it won't fluoresce, right? So if I had all the atoms in that state, and if I somehow, some way, and we'll remind ourselves a way to prepare that state, I prepared the atom, a gas of atoms in that state, and I passed a laser beam through it, I would see no fluorescence, because there would be no absorption, and there would be no photon scatter. You're dark to me, dark to the hand, all right? So that's what we mean by the dark state. So for example, if these two amplitudes were equal, thank you, Omar. If those two amplitudes were equal, if I'd chosen the amplitude of the laser and the dipole matrix element such that the two Rabi frequencies were equal, then the dark state would be a antisymmetric superposition of the two, okay? So if I had prepared that state, if I had chosen the amplitudes and that measure that way, that state would be the dark state, okay? So the other thing that we talked about is that, in fact, let's say I prepared the system in any other state, okay? Suppose I prepared it in some statistical mixture of 1 and 2, which would be the typical state that, say, comes out of a thermal oven, okay? I have some mixed state. What we know is that I'll have some absorb. In that case, I won't have be in the dark state. I will absorb and fluoresce, meaning the atom, if it's here, it can go up here, and if it's up here, it can go down there, and if it's here, well, it could also go down here, and if it's here, it can go up here, and it can fall down, and I'll get this cycle of absorption and emission, and the atom will fluoresce. Those photons will be scattered, and I'll see those photons. And the system will be driven by Rabi oscillations, or it will be driven by the couplings between levels 1 and 2, which will drive population from 1 and 2 into 3, and it will spontaneously emit. And eventually, the system comes to steady state. And what is the steady state in that case? The dark state. Because if the atom were to get to the dark state, it would stop evolving. So that clearly is the steady state of the solution. And the idea of getting to that state is called coherent population travel. It was observed, I think, in 1976. It was the bicentennial, I remember it. We're coming to whatever the assessment, I don't know what centennial it's coming to, 30, 50 years. So I'm older than 50. And you know, that's what was observed. You observed this lack of, and they were vegetarian. Yeah.
So we're saying that long term it's going, the steady state's the dark state.
Yep.
Doesn't that assume there's some path for it to get to the dark
Oh,
state?
that's a very interesting question. That's a very interesting question. And we're gonna study that much more detail. It's very interesting. Now, how in the world does it fall into the dark state? Well, I mean, I can give you a simple example where, let's suppose, and we'll come back to this, let's suppose that omega 2 is 0. Okay? What's the dark state in that case?
Minus C2.
It's this level 2, right? And that's kind of obvious. If I only have this light on and I have this guy, then if assuming there's no other level over here that doesn't exist, then this guy, if it's here, will not absorb any photons. And so I can go like this and I can absorb back, and eventually, through a cycle, ultimately, at the end of the day, all the population will be here, and this state is the dark state. That process of putting all the population into one level that is a pure state is called optical pumping. And the way optical pumping works is to choose the state you want to be dark to the light, so that you pile up all the population in that state. This is how we prepare pure states in atomic physics. This is a kind of cooling. In the sense, if I had entropy and I had a mixed state of some kind, I will purify and I will reduce the entropy and I'll make a pure state. That's a very simple example of getting to a dark state. It's much more subtle when that dark state is actually a superposition. How does this thing fall into a superposition? Because the point is that when the atoms emit photons, they're not necessarily emitting this one or this, they might be emitting a superposition thereof, okay? And then I can fall into a superposition. But it's a very subtle question, and we'll talk about this. Put a pin in it. I'm going to remind you guys about October. What date is this? It's Yom Kippur. I shouldn't be here. It's the 2nd of October. Because you can say, oh yeah, we talked about that in the fall, but I don't remember. But I will have the video to remind you that we did talk about this very subtle question when we talk about the story of quantum trajectories in next semester of how you get to the dark state. But regardless, if you solve the master equation, which you will in your homework, then you see that the steady state solution is, in fact, it's in the notes, the dark state. That is the steady state solution, and it's a pure state. And it's a kind of cooling. Okay? Let me continue. We'll have okay, unless maybe you may want to, yeah, there's a lot to talk about, okay? But I need to skip over just a few hours, and we can just have a chat. I'm just fun. All right, so this is actually an interesting point. I want to talk about the idea. So I want to talk about population transfer. In a lambda system. So we kind of already just said this, but like suppose I was in level 1 and I wanted to get to level 2, okay? And there's no direct transition I can easily drive that takes me from level 1 to level 2. But there is this intermediate level, or 3, that I can get. How would I transfer the population from 1 to 2? Yeah.
Drive from 1 to 3, and keep driving, and let 3 be 2.
Yeah, so this is one way. We just described it. Optical pumping is one way to do that. Yeah.
When you say transfer population, is the...
I say at the end of the day, I want to put, the atom was definitely here, I wanted to put it there.
So whatever, it has to be the same population.
Yeah, I want to take, let's just say that with 100% certainty, I know I'm in level 1, and I want to take the atom and put it in level 2.
Okay.
Okay. So one way to do it is optical pumping, as Nate just reminded, or just we just said, this is the way. Now, we could do that, but depending on what our purpose is, that might not be good, because as we just learned from our homework, we're gonna heat up the atom a lot because we're gonna scatter lots of photons, and the atom's gonna get radiation pressure, right? We just all talked about that in class. So what if I didn't want to do that? How else might I do it?
Could we try an adiabatic following process?
We could. So, well, okay, so there's, what we also know is that I have a way through a Raman transistor. This is what, by the way, this is known as Raman scattering. Because I send in this color light and I get out that color light, that's the Stokes, in the Stokes process of Raman scattering. But we also know we could do, I can think about this. This is spontaneous scattering. I can think about that I'm stimulating, right? I go up to here and then I stimulate back down. Now, as Nate said, there's a lot of different ways I can think about getting from 1 to 2. Yes, Tristan?
Are we intentionally saying little delta is 0 here, or is
Yeah, because in this case, I want to put all the population here, okay? So, and I want to do it in a way that I don't heat up the atom very much. I don't want to have spontaneous emission, right? So I'm going to detune far from the excited state. And we know, in principle, I could do Raman-Rabi oscillations. In fact, I could do a Raman pi pulse. What does that mean? It means I have a pi pulse where I think about this, where 1 is the south pole of the Bloch sphere, 2 is the north pole of the Bloch sphere, and I rotate by pi, right? So if these are the Rabi frequencies and this is the tuning, how do I do that? How much time? I'm going to turn on both of these lasers at the same time. And we know what's going to happen is I'm going to get Rabi oscillations, right? So if I look at the population in level 2 as a function of time, it'll rise. And if I do this such that this is at the peak. So now I'm asking you, how long should I turn these guys on in order to do a pi pulse? I'm listening, but everyone's not quite willing to speak up. Okay, given this detuning, given this these two Rabi frequencies, how long should I wait such that I do exactly a Raman pi pulse? Yes? I'm listening, I'm sorry. Yeah? Oh, so I could do, as you were suggesting, if I did this really quick, I do a quick pi pulse here on resonance, and before it decays, do another pi pulse down here. But I don't want to do that because I don't got enough laser power to do that, because this lifetime's so short. So I want to do this for RF resonance. Yeah, Omar.
It's 2 pi over omega effective, where
Right, so there is a Raman-Rabi frequency. The Raman-Rabi frequency is omega 1 times omega 2 divided by 2 delta. So to do a Raman pi pulse, what I need to do is make this pi. When that's pi, then I have done that. Alternatively, I could do sort of what Nate was describing. We know if I were to look at the dress states associated with the effective 2-level system here, and I looked at this, so now I'm going to allow myself a Raman detuning, a 2-photon detuning. And if I looked at the dress states of the system as a function of the Raman detuning, I get this avoided crossing. And in principle, I can adiabatically start on the red side of resonance, where this, if it's very far off resonance, the state is here, and as I sweep this, I chirp the laser to a higher frequency and go through resonance. I will, if I do it slowly enough, that's known as rapid adiabatic passage. Well, it's interesting that it's both rapid and adiabatic. So we have different time scales. It has to be adiabatic, which means that the rate at which I'm changing the detuning must be sufficiently slow compared to the gap. And the gap is given by the Raman-Rabi frequency. So it has to be slow compared to that, but fast compared to the scattering rate. The scattering rate is the rate at which, well, I might sometimes absorb some photons and then I'm screwed, and then I've lost coherence. This goes like 1 over the detuning. The scattering rate goes like 1 over the detuning squared. So there's room to spare. I can be fast compared to one thing and slow compared to the other. Now, why would I do an adiabatic passage versus a pi pulse? Well, adiabatic passage is a little more forgiving too. As long as it's adiabatic, doesn't matter exactly what the amplitude is. If the amplitude's varying a little bit, that'll change these curves. But so adiabatic passage is a very robust way to do the transfer compared to a pi pulse. Depends how well I got my laser system working so far.
Can you repeat it's rapid compared to the
It's got to be slow compared to this, which is the gap, but rapid compared to the scattering rate. Remember, the scattering rate is this, which is proportional to 1 over the detuning squared. Okay, so I can have that. I can be fast compared to that, which can be very, very much slower than this. Okay, so I got to be far off resonance to make this work. Okay. But there's yet one other way, which is completely crazy, which is known as Stirap. Which is stimulated something Raman adiabatic. This is stimulated Raman adiabatic passage. Okay, it's not quite this. And this is using dark states. Okay? So, what we were just thinking about when we thought about transferring from 1 to 3, the intuitive thing is, okay, first I'm going to turn on laser 1, which brings it up to 3, and then I can stimulate it down from 3 to 2. That's one way to do it. Or we had this kind of Raman-Rabi oscillations. But let's think about the following counterintuitive pulse sequence. So, as a function of time here, I'm first going to turn on laser 2. This is the Rabi frequency amplitude as a function of time. So first I'm going to turn on this laser. There's nothing there. And then I'm going to turn on laser 1 with this pulse in the opposite order. First I do 2, and then I do 1. I have a pulse of that. The claim is that, and I'm going to do this on resonance.
no detuning?
No detuning. So this is an advantage of doing things this way. It's much faster because I'm on resonance. The problem with this is that I get a lot of spontaneous emission. But by doing stirrup, as I'm going to explain to you, I can be on resonance and have no spontaneous emission at all. Okay? So, well, what? So the first thing here, so this is stimulated Raman adiabatic passage. But it's not quite the kind of adiabatic passage I just described to you here. It's in a different, this I had both lasers on at the same time and I was just sweeping the detuning. Here I'm not doing anything with the frequency, I'm just changing the amplitude, okay? The Rabi frequency is the amplitude. So I have two pulses. Why does this work? Well, this is related to dark states. So let's go back and think about this process. Maybe I'll draw it here. So when I'm out here in the wings, I'm going to draw a three-level diagram. At these very early times, what is the dark state? State 1. Right here, that's the light. This guy's dark. Okay?
Are we assuming the omega 2 pulses on at the moment? Or?
Yeah, I started in state 1, and now I turned on laser 2, and I'm asking, as this is rising, before I see any appreciable laser 1, so I have this guy is the dark state, okay? When I'm right in the middle, well, let's say I'm over here, where I have a little bit of laser 1 and a tiny bit, and a lot of laser 2. Remember, somewhere over here, there's the dark state. Okay? So, in this case, when I'm over here, I have a tiny, so all the amplitude is here at this point. Now I have a tiny bit of amplitude here, but most of the amplitude is here. Okay, when I'm at this point. What's the dark state there? It's mostly 1, but I put a little bit in 2. The dark state in that case is a superposition where the vast majority of the pop field amplitude is here, but there's a tiny amplitude here. When I'm at this point, what does it look like?
Populations in state 1 and state 2.
Now they're equal, omega 1 and omega 2 are equal, and at this point, I have the situation where I have an equal superposition of the two. And when I'm all the way in the wings over here, where only laser 2 is on, and there's no laser 1 at all, I'm sorry, in this case it's all laser 1. Yeah. I'm sorry, my pictures are weird. This guy is all laser 2. This guy is mostly laser 2 with a little bit of laser 1. This guy, they're equal. In this guy, I'm all laser 1. I'm no laser 2. What is the dark state at the end?
So if we're steady, if each one of these time steps is steady state, then
Right. So it's not about the steady state. It's about adiabatic. I'm going to come to this in a moment. I'm going to come to this in a moment. But if I can rotate my state in Hilbert space in this way, I started in a 1 and I ended in 2. And I did it in such a way that at every step of the way, I was in the dark state. Then I can do an adiabatic passage which takes me from level 1 to level 2, where I was at all times dark to the laser. So let's just, before we let's just think about the math about what do I mean. Let's write down again the atom laser Hamiltonian. As we did last time, I can rewrite this as the following Hamiltonian, where the bright state is the thing that is orthogonal to the dark state. Okay, so this state is orthogonal to the dark state. This we call the bright state. Why is it bright? Because this state absorbs. If I started in the bright state, I would Rabi oscillate to the 3 state with this Rabi frequency. Okay? So, now I ask you, what are the dress states of this Hamiltonian? Okay? What are the dress states? The dress states are the eigenstates of this 3-level Hamiltonian. This Hamiltonian, which we could write down as a matrix. We're going to do it for homework. We could diagonalize it, and we could find its eigenvectors and eigenvalues. However, I'm helping you with your homework. You can do it by eye, because look at this Hamiltonian. Firstly, I claim there's one obvious eigenvector of the system. What's that? No, 3 is not an eigenstate. 3 is coupled to B. Yeah.
In the bright and 3 basis, isn't that just the x?
That's right. That's a less obvious one. But I claim firstly that what is this?
0.
0. The dark state is an eigenvector of the Hamiltonian with eigenvalue 0. But the other 2 eigenvectors are exactly as, so the dark state has eigenvalue 0. There are 2 other states, plus and minus, which are eigenvectors. What are they? These are the ones that Tristan was suggesting.
The superposition of 3 and right.
That's right. So I have 3 plus or minus, right? Those are the eigenvectors. These are the 3 eigenvectors of the system. And the eigenvalue of these guys are that. Plus and minus that, right? So those are the 3 eigenvectors. And the eigenvalues are this and 0. So as a function of time, as I turn on and off these pulses, what do the dress eigenvalues look like as a function of time? Firstly, there's one eigenvalue that's always 0. This is the dark state, and it has no light shift because it doesn't couple at all. Okay? Way back at negative time, the state was 2. At this intermediate time, right at the origin, it's the superposition of 1 and 2. That's when I have equal amounts of omega 1 and omega 2. And over here, the state is 1. This is the dark state as a function of time. We just said the dark state is a different state, a different time, because there's different amounts, and we can see that, okay? Whereas over here, there is a state that is the plus state, which is the superposition of the bright state and 3, and then there's, look at me being fancy. This state, which is the minus state. And so, similarly to what we did with Raman adiabatic passage, if I start in the dark state and I have this counterintuitive pulse sequence where first I turn on the light that does nothing and then I do the other light, I will move along this pink curve and adiabatically move from 2 to a superposition to 1. All the time being dark. Amazing. Yes, quantum mechanics, I love you. Yes.
So, the reason I thought of the word steady state was
Yeah.
because the dark state is, it settles to steady state.
It
To the
would
dark
if I started, so you're right, if I started in any other state other than the dark state, and I turned on the light, and I didn't do anything, in steady state it will go to the dark state through optical pumping.
Right, and so different.
But here I'm not optically pumping. I started in the dark state. I am at this point, I am in level 2, I turned on light, it's the other way around.
I was just gonna ask.
Yeah,
You're in level 1 and going to level 2.
yeah. I'm in level 1 going to level 2. So here, I turned on light 2, and this was dark. There's no steady state because it's not absorbing anything. What happens is I'm changing the relative strength of these 2 lights, and this guy will then coherently rotate in Hilbert space with no steady state, no spontaneous emission at all. It'll rotate from 1 into a little bit of 2, into an equal superposition, into a little more 2, a little less 1, and go all the way. Yeah, Andy.
So what about this is adiabatic? Is it just the fact that we're saying it is an eigenstate?
So the question really here is, in order to do this, I have to as I change the system in time, the question is, how does the state of the system change? Okay, I have to solve the Schrodinger equation. The fact that I'm saying it stays along this big curve is what's known as the adiabatic theorem. The adiabatic theorem says if I'm in an eigenstate of the system, but the Hamiltonian changes, I stay in the instantaneous eigenstate. If my evolution is slow, which means that I have to move this slower than the gap. Otherwise, I'm going to populate these guys, and at that point, all bets are off, I'll spontaneously emit. So the adiabatic theorem says the solution to the Schrodinger equation is the energy eigenvector of T. So if I have an energy eigenstate, and the energy eigenstates are different at different times because the Hamiltonian is a different thing at different times. This is only true, this is the solution to the Schrodinger equation, only if the Hamiltonian changes slowly enough. Yeah, otherwise, that's not the solution. Donald, then Omar.
What labels the eigenstates if, well, we start with, say, 1, and then 1 minus 2, and then 2?
They are labeled by this. So let's maybe write this a little bit more clearly. Here are the three eigenvectors. Let me use this fancy. Okay? Whatever, I hate. All of these things are functions of time. Because with time. So I have eigenvalues and eigenvectors at different times because omega 1 and omega 2 are different at different times. So at the initial time, the eigenvectors are 1, 2, and 3. 2 has eigenvalue 0, and 1 and 3 are connected as a two-level system, and this would be 3 plus or minus 1. Later, the eigenvectors are 3 plus or minus 2 and 1. So I'm adiabatically changing what is the dark state and what is the bright state. But if I started an eigenstate of the Hamiltonian and I change the Hamiltonian really, really slowly, it's like, here's adiabatic classical. I have a marble in a bowl. I don't want to excite, I want to keep it in the ground state. How do I do it? I got to move the bowl really. If I start moving fast, it starts moving, that's not adiabatic. But if I start in the ground state and I change the Hamiltonian slowly, I stay in the ground state. And I would stay in any eigenstate. That's the adiabatic theorem in quantum mechanics.
So you change from 1 to 2 and you do it slowly. Is this lower than the other two transitions?
No, it's actually faster because I'm on resonance. You see, here I had to be slow compared to this thing, which went like 1 over the detuning. So the Rabi frequency wasn't very big because I was far detuned. This is done on resonance. It's done on resonance, but with no spontaneous emission. Kind of crazy. And it's done backwards. Yeah?
So the reason there is no spontaneous emission is because my evolution never goes after the tree, right?
It can't,
Yeah.
because the dark state is uncoupled. The only thing that's coupled to 3 is the bright state. Isn't that crazy? Yeah.
So what's the time scales for the dark state?
Well, here, this gap here, which is omega 1 and omega 2.
Oh, I see. So it's omega 1 times omega 2.
Over delta.
I see.
Over delta. That's the problem.
I see.
Now, this, of course, requires this special timing. I don't think mostly this is what people do. I don't know. Ask your friends in the laboratory. Yes?
So then at very early times, my bright state's going to be just second eigenstate.
That's right, but there's nothing there.
Right.
So it doesn't do anything. What's happening here is as so at this point, I could have cut this off. Nothing was really important until that point when this thing started to turn on. At this point, I start to create some coherence between 2 and 3 that makes this whole thing dark. All right, I'm gonna let you guys think about all of that. You're gonna do your own. this is the whole problem. I just did it because what? Because we have to do it. All right, such a beautiful thing. So this is one very interesting use of the dark state, is theoretic. I want to talk about one other incredibly interesting use, which is known as electromagnetically induced transparency.
But I have a question.
Yes, I'm gonna say.
So we're in a dark state, and then we have these Rabi frequencies 1 and 2.
Yep.
And you go, I mean, you do a pipe pulse. But what if I want to add a phase to that? What if I want to end in a state where I have a phase, maybe like a white?
Well, so of course the phase that's accumulated, we have to think a little bit more careful about the Schrodinger equation, right? So, as Tristan reminded me on some other reason, when we do a pi pulse, we actually have an I phase that's induced. If I did a Raman pi pulse here, I get an I phase. If I do adiabatic, I have to think about the dynamical phase, which is e to the minus I, whatever the eigenvalue is, dt, from 0 to the final time over h bar. That's called the dynamical phase, okay? And now in this case, there is no dynamical phase because this thing is a 0, right? There's also a Berry's phase, that's a whole other story, but I'm not going there. We'll talk about that offline. All right, I want to talk about this. So, let's just remind ourselves, again, if I have a two-level system, let's call this one ground and excited, and I have some detuning, I'll call it, because in my notes I called it little delta, I'll call it little delta here. This is say my excited state. Then we know in this situation, if I looked at polarizability, the imaginary part is a Lorentzian, and the real part is this dispersive line shape. So this is the complex, this is the imaginary part. This is the real part. If I thought, and it looks like as long as my Rabi frequency is sufficiently small that I have little population in the excited state. So when delta plus I down over 2 is much, much bigger than omega, I have this linear response. It looks like a Lorentz oscillator, right? And it has a line width that depends on the rate of decay of the excited state, and I get maximum absorption right on resonance, okay? So that's for a two-level system, and we solved that, right? From the master equation. Now let's look at a similar situation where I'm gonna have the following thing. I have a third level, okay? And that third level, I'm going to very strongly couple it on resonance with some coupling laser, okay? And now I'm going to probe the absorption. So I start all the population here, and I have what I'm going to call, this is the coupling laser. And another laser I'm going to call the probe laser, which has a particular Rabi frequency. And I'm going to scan this through resonance. And I'm going to choose my coupling Rabi frequency to be absolutely huge compared to the probe, okay? So if I didn't have this over here, I'd have this. What we're going to show in a moment is what we have in this case is the following. So this is my imaginary part of alpha, and this is my real part of alpha. The response, the dipole response, is completely changed near resonance. Notice what happens right on resonance when delta is 0. Right on 0, right on resonance, this is 0. It's transparent. It doesn't absorb at all. And that transparency was induced electromagnetically by coupling it to level 2, hence the name, EIT. In addition, and we'll come back to this, the real part of alpha is crazy here. It has this incredibly sharp feature here where the real part of alpha, which is related to the nth refraction, changes very rapidly right in the transparency window, okay? Which means that this is a very weird kind of nonlinear optical response. Yeah?
Is it going through 0 at the same point?
It is. It goes through 0 right at the origin. Also, the whole thing, the real part is also 0. But what's more important is its slope, as we'll see in a moment. Okay? So, yeah.
I imagine you're assuming that the coupling laser is far more intense than the probe.
I am. That's what this means.
Yeah.
Okay? Yeah. What's really important is the Rabi frequency, the dipole matrix element, but the intensity is certainly part of it. Remember, that's DI. Okay. So what's going on here? Well, in the same way, I want to come back to remind us when the reason we have this dark state in the first place is a kind of interference. Quantum interference. It's quantum interference comes from coherence, comes from the superpositions. So we had this dark state when we had these two states because there were two different processes which this atom could absorb. Either it could absorb that and absorb that, but if I had a superposition, those two paths destructively interfered. It's the destructive interference which is why there was a dark state in the first place. Okay. So if there is this transparency and the absorption goes to 0 at that point, there is also some kind of interference that is going on right on resonance. Okay? And we can think about that in a number of different ways. One way to think about it is, again, to think about elementary processes by which a photon is absorbed or emitted in some way. If I start in level 1 and I get to level 3, I could do that right on resonance directly. So that's doesn't matter what I'm calling the higher one, but I'll just consistent. So if I start in level 1, that's one process. That's the usual absorption. But if I have this coupling laser, there's another thing that can happen. I can think about it this way, which is that I absorb, I stimulate, emit, and then absorb. It's a 3-proton process involving absorption of this photon, the probe photon, stimulated emission of photon 2 and reabsorption, but it's a possible way I can get from 1 to 3. And if these guys destructively interfere, I got no absorption. So that's one way to understand electromagnetically induced transparency, but actually I don't think it's the best way. That's interesting. The law of large numbers. One of my favorite laws. You know, I'm surrounded by lawyers. My partner's a lawyer, his daughter's a lawyer, her husband's a lawyer, they have 2 parents. Anyway,
you ever need to write a strongly worded bill.
So I don't need the lots of numbers, I got lawyers anyway. Anyway, all right, so let's look at now the mathematics of this kind of thing. So what do I want to do? What I want to calculate is the dipole response. What is the induced electric dipole on the absorption, on the transition between 1 and 3, okay? So I want to know what is the induced dipole moment you may be the probe, okay? That depends on the coherence between level 1 and level 3. Because it's the superposition of level 1 and level 3 that is the induced dipole, okay? So we want to calculate what this is in steady state, in the same way that we did for the 2-level atom, okay? So let's remind ourselves of this. Okay, so the effective Hamiltonian in the rotating wave approximation. So that's level 3. Level 2 has the same detuning in this case. So I could also write this like this. That's minus the detuning. Either way, I can think about it as the same level diagram. Everyone want to see that? And then I have the Rabi coupling. So level 1 is coupled to level 3. And level 2 is coupled to level 3. But, oh, this one I'm calling the probe, and this I'm calling the coupling. And so, if I look at the Schrodinger equation for the different amplitudes, bless you. These are equations we've written before. They include the Rabi coupling between the two ground states and the excited state, and the appropriate detunings and decays. Okay? And from this we can get the equations for the coherences with little population. The excited states, so I'm going to ignore the refeeding term. So rho 3,1 is the time derivative of that element of the density matrix. So that's equal to C3 C1 star dot plus C3 dot C1 star. The algebra is boring as hell. Who cares? Let's just get to the answer. Let's first take a look at this equation and try to understand it. So, if I didn't have the coupling laser on, this is the familiar optical block equations, which tells me that the coherences are coupled to the population inversion through the Rabi oscillation, there's a detuning and decay. That's just like we had for the two-level atom, and we've been studying for some weeks. But now that we have the coupling laser, we have this interesting term, which says that the coherences between level 1 and level 3 are related somehow to the coherence that's generated between the two ground states, between 1 and 2. So we need to find that equation of motion. Which is equal to I delta rho T1 minus I omega 2, or not omega 2, omega coupling omega 3, 1 plus I omega probe over 2 rho 2, 3. Okay? That's just once you do the algebra. But we're going to make a couple of assumptions here. One is we're going to assume this, which is to say my probe Rabi frequency is sufficiently weak compared to both delta and gamma that I get very little population in the excited state driven by these things, okay? And secondly, we have this assumption that our coupling laser is way intense compared to the probe laser. Yeah?
What were the C's coefficients on again?
Remember what we said, we have a Schrodinger equation, which these are the probability amplitudes in the three states. So I'm just writing down the Schrodinger equation based on the effective Hamiltonian that has an imaginary part. That's what I'm doing. It's an easy way to get the master equation. Okay. So with that, what I'm saying firstly is that since this is much stronger than this, I'm going to neglect that, okay, because of this, that this is a huge number compared to this. Moreover, because I have this weak driving, that's to say I'm in the linear response regime where the probe, it's only going to be a response to first order in the electric field. There's very little population 3 compared to the ground state, so I'm going to neglect that. Okay, so those come from those two approximations. Yep.
Are you able to cancel out the minus I pro divided by 2 P11?
No, because I want to look at that. Otherwise, I won't have any response at all to the probe. I want to keep things to first order in that relative to this. Otherwise, there's no response at all. And it would never get anywhere. So, with that, I can solve these equations in steady state. And the two equations I get are the following. I get that rho 3,1 is equal to the probe over 2 divided by delta plus I gamma over 2. That's just the first term. That's just like what we saw. This is the linear response that we saw for the two-level atom before. Plus the coupling over 2 divided by delta plus I gamma over 2 rho 2,1. Okay, so that's just the solution. That's just writing down this equation and looking at it in steady state. This first term is what we saw for just the two-level atom, but now we have this extra term. And in steady state, rho 2(1) is equal to, assuming I can neglect the effect of a probe on it, is equal to omega coupling over 2 delta rho 3(1). Okay. So now if I can plug this back into here and solve. Yeah.
There's supposed to be a row on the first term as well.
Yes, I'm sorry. This is approximately equal to 1, right? Yes. It's first order. There'll be, it's 1 over 1. It's 1 minus the saturation parameter, but it's 1 for the lowest order. Yes, thank you. Okay, so now I plug that back in, and I solve for rho 3(1), and I get the following expression. The probe is the dipole matrix element E31 times E laser 1 over 2H1. So this tells me that the induced dipole complex amplitude is equal to minus the dipole matrix element squared, because the I need to multiply by the dipole matrix element to get that, over 2H bar divided by delta minus the coupling laser Rabi frequency square over 4 delta minus I m over 2 times the probe electric field. So let's stare at this at the moment. If the coupling laser was 0, if I had no coupling in between 2 and 3, this would be 0. This is my polarizability. It's the linear polarizability. It's how much induced dipole moment I get relative to the strength of the electric field. Okay? When this were 0, that's our complex Lorentzian. That's our friend, this, whose real and imaginary parts were the dispersive line shape and the Lorentzian line shape, right? But what the heck does this do? How are we going to? So let's take a look at this polarizability. Let's just look at this function. Firstly, well, how would you try to sketch that? You don't have your graphing calculator, you're on a desert island, there's no Google, ChatGPT around. You just gotta sketch this because you gotta get off this island, know that it's the only way you're gonna get off. Well, what we do is we look at the limits, right? When delta is really, really big compared to this number, I can ignore that. And in that regime, it looks like the same thing because it can be ignored when this is huge compared to this, okay? But when delta starts to become very small compared to this thing dominates, right? So in the limit, when delta is much, much smaller than or delta squared is much, much smaller, or delta is much, much smaller than this over 2, then I can ignore that term and then I have this. And what happens to this in the limit that delta goes to 0? Well, the imaginary part of this is going to be this over that plus that. So let's think about the real and imaginary parts of this function. So in this regime, when delta is much, much smaller than the coupling laser over Rabi frequency over 2, the polarizability is approximately equal to, well, there's this minus sign that was from, I'm going to put the minus sign out there because that's from the dipole. So this would be minus, so this will be, the imaginary plus will be plus gamma over 2 divided by and the real part is over the same denominator. So what is this in the limit that delta goes to 0? Well, in the limit that delta goes to 0, this is huge compared to that, right? So I can ignore that. And it's going to be proportional to delta squared, which is a parabola, right? It's 1 over that, the delta squared goes in the numerator, and it goes to 0. At delta equals 0, this goes to 0. And then there's a parabola which has a width. The width of this thing goes like omega squared over delta. So I can have a transparency window there, and it becomes exactly transparent. Right on resonance, the imaginary part of the polarizability is 0. The real part, on the other hand, has this very sharp feature to it. And that's interesting unto itself. Now, before I do that, I want to say one other thing about the thing I erased. There's another way to think about electromagnetically induced transparency, which I think is the better way. When I have these two states, and I have this strong coupling, this guy isn't really coupled to this or this, but it's coupled to some superposition of 3 and 2 that's induced by the coupling laser. Which means that really my level diagram looks like this. Split by, these states are the dress states. They're the eigenstates of the system that includes this coupling. There are 2 dress states, the symmetric and anisymmetric coupling, that are split by the coupling laser Rabi frequency, because that's the splitting of the dress states. And when I'm right on resonance, well, I couple equally to this and this, because I have, or this should be over root 2. I have equal amount of amplitude in 3. One only couples to 3. But in one case, I'm to the red of resonance, and in one case, I'm into the blue of resonance. Which means the dipoles are 180 degrees out of phase with one another, and they destructively interfere. It's the destructive interference between these 2 paths to the dress states, that is, gives rise to EIT. This is known as Fano interference. Ugo Fano was a great atomic physicist of, I don't know, the 1960s, who first discovered this in the context of autoionization of helium atoms, where there was an interference between an unbound and bound states that led to a change in the scattering cross-section. But this is what we have. Really, I think the best way to understand what happens in EIT is that there are two dress states to which I can absorb, and there is destructive interference between them. And if that right on resonance, because I'm equal amount to the red and the blue, the dipoles are oscillating 180 degrees out of phase one another, they destructively interfere. Oh, we don't have time, but I maybe just mention one thing, and you should read about it in the notes, which is, what about the real part? Well, the real part, because remember, the index of refraction of the system is 1 plus 4 pi times the susceptibility, or the density of atoms, times the real part of the polarizability. Those of you who studied in and with me last semester may remember that, or maybe you forgot. N is the density of atoms. So we have the phase velocity, which is C over the index of refraction. And we have, which is omega over K. So K is equal to omega over C times N. But then we have the group velocity, which is omega, the omega dk, which is dk, which is 1 over dk d omega. So if the index of refraction is changing very rapidly with frequency, the group velocity is really, 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 really small. In fact, in this thing, there was a famous experiment done in 1999 where they did EIT with sodium atoms, and they put a pulse in on frequency, and the light went at 17 meters per second, which is about how fast I ride on a bicycle. And this is what's called slow light. You have an incredibly big, the group velocity is much less than the speed of light, and it's one of the ways that you can think about making a memory to slow down the light to the point that you can stop it, put the light into the excitations of the atom, and then retrieve it later. There's lots of experiments where people are trying to do this kind of thing. But it all relies on coherence. This is our show, this kind of quantum interference.
So delay lines make a reappearance after.
Yeah, I mean it's not a delay line. This is nothing. There's no. I usually you rock a lot of optical fiber, and that's it's just rattling around. Here it's that you're slowing it down. You're putting all of the energy into the atoms, into these dress states, and then you have to release them by changing these coupling and probe and coupling so we can release the photon later.
Want to know what a polariton is?
Yeah, that's what a polariton is.
Yeah.
Yeah. All right. Very good, Hank. We'll call it there. We'll call it a day. And we're now done with what we're going to talk about this semester relative to atomic coherence and interference that arises from superpositions of atomic states. And starting on Tuesday, and then after fall break, we'll start talking about the coherence in the light itself from the quantum, and we'll quantize the field. So we'll start talking about quantum field theory on Tuesday. All right, I'll get after you.
Yeah, I know.